So we're moving into friction. And remember again that friction always acts against the motion or potential motion of an object. And there's two types of friction. We introduced this at the beginning of the unit, but I just kind of remind you of it. Kinetic friction is between two sliding surfaces, and static friction is between two stationary surfaces. Interestingly enough, the force of kinetic friction, F sub k, is just equal to the coefficient of kinetic friction times the normal force. Again, where do we get this number from? Usually from a table. Normal force we've talked about before. Static friction, on the other hand, is a little bit more interesting. It can vary all the way between 0 up to some maximum value, which is given by the coefficient of static friction, mu sub s, times the normal force. This quantity right here is that maximum force. You might remember we did shoe wars a while back. If you have a shoe sitting on a track and the track is completely level, there is no force of friction between the shoe and the track. Forgive my shoe. Put some laces on it so it looks like a shoe. There is no force of friction. So at that point, the force of static friction would be 0. But as I lean the track up, the force of static friction has to get larger and larger, acting against the slide or potential slide, so that the shoe stays in place. And the force of static friction would be acting up this way, as long as it's not sliding yet. And that's going to have to get larger and larger to balance the component of the force of gravity that's trying to push it down the ramp. Again, remember, just a quick reminder, force of gravity is acting straight downward. For things on ramps, we typically break them into components that are acting parallel and perpendicular to the ramp. So in this case, if we break this into its perpendicular component, acting this way, and its parallel component acting this way, the force of static friction up here is going to have to match this component down here. At some point, though, you're going to tilt the ramp so far that the shoe begins to slide. At that moment, you've exceeded this maximum force of static friction. This force of static friction up here no longer can match that component of gravity. The moment it starts sliding, we switch back to kinetic friction, which is just given by this. This is a nice illustration of that. Static friction can vary anywhere between 0 up to a maximum. As we tilt that ramp up further and further, force of static friction gets larger and larger. But the moment you exceed that maximum force of static friction, I called it F sub s max here, which again is equal to mu sub s times the normal force. That's the absolute maximum the force of static friction can be. That's when the shoe begins to slide. And at that instant, we move into the kinetic area. And at that point, we're dealing with kinetic friction. And kinetic friction has just a single value. And you'll notice here that this stays level. That's the force between two sliding surfaces, and it has just one given value. That's given by mu sub k times the force normal. And you might say, oh, wait, this is super simple. Yeah, it's just a little exciting. The force of static friction can vary anywhere between 0 up to this maximum value. So it's less than or equal to that. The moment you exceed this, you switch over to kinetic. Here's a nice quick illustration of that. You've got two vehicles here, one with anti-lock braking and the other one does not. But watch what happens here when they apply their brakes. And this is a simulation, but it's the same idea.
Both drivers apply their brakes at the same time and with the same force.
So the top car here has ABS. Here, notice that the wheels stop moving. And so it has less friction because we're dealing with the kinetic friction here. The car on top here is still rolling at every single point, which means you're dealing with static friction, which has a larger maximum force than the force of kinetic friction, which means you can stop more rapidly and also keep control. Take a quick look at this table. I just want to I want you to notice this. What's the relative sizes of mu sub s and mu sub k for a given set of surfaces? And for almost all of them, you'll notice that mu sub s is larger than mu sub k's for the same materials. There's only one exception to that rule in this one, and that is Teflon on Teflon, where it actually matches. But for everything else, typically you end up with a much smaller mu sub k than mu sub s. So one quick practical problem. If the mass of this penguin is 10 kilograms and the coefficient of, or mu sub k, is 0.04, what's the force of kinetic friction? Let's just make gravity 10 for this one. And so you can very quickly work out the force of gravity is going to be 100 newtons. And the normal force is going to be 100 newtons as well. And the force of kinetic friction then, which is acting against the motion of our penguin, is just going to be equal to mu sub k times the normal force, which in this case is going to be the coefficient of kinetic friction, 0.04, times our normal force. Sorry, it takes me longer to write this than it is to solve it, times 100, or it's going to be equal to 4 newtons. So that is the force of friction between this penguin's skis and the ground, or and the snow in this case. The second question is, what's the acceleration of the penguin? Well, to answer that, we just have to use F net equals ma. And for some odd reason, a lot of students think, oh, I've got to somehow worry about the normal force and force of gravity. But again, these two are equal and opposite, and they're vector quantities. So they actually, you can think about them as being canceling out. Solving this one, the only net force I have on my penguin is this 4 newtons. I'm going to leave off units. Our mass of our penguin is 10 times the penguin's acceleration. And you'll get an acceleration then of 0.4 meters per second squared. Now, a quick warning about this. You're like, wait, didn't we do the math right? Yeah, we did the math absolutely correctly. But is our penguin gaining speed, or are they losing speed? Are they gaining 0.4 meters per second every second, or losing that? The answer is they're slowing down. So this should be negative. And you might say, wait, how in the world am I supposed to know it's negative? Well, one is pure logic at the end here. Or you could also realize that this 4 Newton force over here is technically acting against the motion. You could say it's negative 4 newtons. It's impeding or slowing down the motion of this thing, so it's acting against the motion. It's going to create a negative acceleration. This one's kind of fun. So in this case, a quick note on this one, this box is moving at a constant velocity. Draw a free body diagram for the crate. Well, I'm going to do that, except I'm kind of out of space, so forgive me, I'm just going to draw it on the actual crate, just for clarity, so you know what each force is. They're applying a 100 Newton force. That's a tension in this cable. And remember, the first thing we're going to do whenever we have a vector acting at an angle, we're going to break it into its two components. And so the vertical component of this tension, and we have a horizontal component of this tension. I'm just going to go to 2 sig figs on both of these. This is going to be 50 newtons, just using 100 times the sine of 30, or if you remember your 30, 60, 90s. And this side should be, I'm going to call it 87 newtons. 100 times the cosine of 30. And now we can draw the other force vectors on this thing. What do we know? We've got the force of gravity. And again, I'm going to make G equal to negative 10 meters per second squared. So the force of gravity in this case is just going to be 300 newtons acting downward. And there has to be a normal force, but be careful on this one. Everybody's like, oh, the force normal is going to be 300. Yeah, it would be, except for one detail. This person's tension is actually pulling this thing up with a force of 50 newtons. So how much force does the ground need to provide to hold this thing up? The answer is only 250 newtons. Remember, the net force here has to be 0 because it's constant velocity. We have 50 acting up this way, plus the 250 acting up this way equals the force of gravity 300 that way. Finally, there has to be a force of friction acting this way. And you might say, wait, how do we know that? Well, we know the block is sliding, so it's got to be kinetic friction, and it's sliding to the left. What does the force of kinetic friction have to equal in this case? Well, we know the net force has to be 0, and I've got 87 newtons acting towards the left. This has to be 87 newtons acting to the right. I'm trying to fit it in here real quick. So that the net force is 0, so we move at a constant velocity. You're like, okay, good, I've got my force diagram done, all my forces identified. Free body diagram, I should actually draw a dot for the crate and then draw all these on here, but I thought it might be easier to visualize this way. The second part of this, though, is, hey, what is the coefficient of friction? Well, we know the force of kinetic friction from the equation up here on top has to just equal the coefficient of friction, which we don't know, times the normal force. Well, it turns out we know everything in this one except for a mu sub k. So plugging in our numbers, we have 87 equals, and again, leaving off units, mu sub k times the normal force, which is 250. Dividing this, you end up with mu sub k, oh, rats. Grabbing my calculator because I'm worried. 87 divided by 250 gives us about 0.35. And there are no units for the coefficient of friction. It's newtons divided by newtons, so it's a unitless quantity. Moving on. Take a look at this one. A 60-kilogram skier is moving at 10 meters per second when she encounters some wet snow that slows her to a stop in 25 meters. Draw a free body diagram. First question is, what's her acceleration? Well, let's do the free body diagram real quick. We know the force of gravity on her is going to be 600 newtons. And in this case, there's no upward force on her. So the normal force, again, is going to be about 600 newtons. Which way is friction acting on her? Well, it looks like she's heading towards the left. Friction always acts against the slide or potential slide of an object. So our final force on her should be the force of friction acting to the right. And in this case, it would be, again, kinetic friction because it's between two sliding surfaces. But we don't know what it is yet. So how do we solve this? So we've got our free body diagram, but without numbers. The next question is, what's her acceleration? And you might say, whoa, wait a second. How are we going to know that? We can't figure out the net force. We can't use F equals ma because we don't know the force of kinetic friction. Well, believe it or not, we know enough information here. She encounters some wet snow that slows her to a stop in this distance. Believe it or not, we can use some of your old equations. If you remember this one, V final squared equals V initial squared plus 2 times the acceleration times delta x. We can use this to figure out her acceleration. Plugging in our numbers, her final velocity, she comes to a rest, is going to be 0. Her initial velocity is 10, so 10 squared, plus 2 times the acceleration, which we don't know yet, times the distance this is happening, and that answer is 25 meters. So if we solve this 100 divided by 50, her acceleration, and mathematically this works out perfectly, you'll get a negative sign when you solve this one, will be negative 2 meters per second squared. So that answers this question. And then finally, the not finally yet, but next question is, what's the net force on her? Well, F net equals ma. We know her mass. I'm going to leave off the net. We know her mass is 60. And we know her acceleration is -2. And you could just put in 2 as well. It doesn't really matter in this case. But I'll put in -2, because in this case it actually does kind of give you expression. The net force on her must be -120 newtons, which means there must be 120 newtons acting against her motion. Some of you will see this immediately. Others of you are like, wait, what? Which, believe it or not, you can now tell me what the force of kinetic friction is on her. You're like, what? Yeah. What is producing that net force on her? Well, the only unbalanced force, only force that you're going to end up with, is this force of kinetic friction. And it is going to be equal to 120 newtons acting against her motion. That's that negative sign you saw before. Last step. We need to find mu sub k. What am I going to do? I am running out of space. We know that the force of kinetic friction is just equal to mu sub k times the normal force. And we actually know all of these quantities except for mu sub k. So in this case, the force of friction is 120 newtons, leaving off units just for speed, equals mu sub k, and our normal force is 600. Dividing both sides by 600, you get mu sub k is 1/5, or 0.2. Again, a unitless quantity. Good. You're like, Ms. Clomber, that doesn't match the mu for skis on snow. Yeah, this is wet snow, technically, so we don't know what the mu is ahead of time, so it doesn't match the table you saw earlier. How about this one? This time the skier is on a slope. And we're given the mass of the skier. So let's do the easy parts first. Force of gravity is going to be 800 newtons. And again, when we're dealing with things on slopes like this, we always break it into its components that are perpendicular and parallel. Forgive me for a moment as I double check to make sure my numbers are right. Okay, yeah. If we break those into two components, you'll discover that this component that's perpendicular and the component that's parallel to our slope are going to be the exact same magnitude. What are they going to be? If you do your trig real quick, this angle here is 45 degrees. They should be about 566 newtons each. Double checking my numbers, yes. And once we know those, we can immediately identify what the normal force is on our skier. The force normal here is going to be equal to this component of gravity that's trying to force the skier into the slope. So it's also going to be 566 newtons. And then finally, they give us the coefficient of friction between the skis and the snow. There is friction acting this time, and which way is it acting? Well, friction always acts against the slide or potential slide. In this case, the friction is going to be acting up this way. What's it going to be equal to? It's going to be equal to, and I probably can't write it up here. Oh, I'm going to try. It's equal to mu sub k, 0.04, times the normal force, which is that 566. And if you solve that, taking my previous answer times 0.04, we get it's about 22.6 newtons. Sorry for writing above it. And so we answered the part here, what's the force of kinetic friction? It's this. And then there's a second part of this one. What's the acceleration of the skier? Well, now we can actually solve F net equals ma. And you've got a component of gravity that's trying to accelerate the skier down the slope, but you also have the force of friction that's opposing that. So what's the net force on the skier? Well, we've got this going downward, this acting against it. That's supposed to be an arrow. There we go. So the net force in this case is going to be 566 minus the 22.6. Equals the mass of our skier, which is 80, times her acceleration. And I got to grab my calculator real quick. If you solve this, the 566 minus the force of friction divided by 80 gives us about, I'll just do the 2 sig figs, about 6.8 meters per second squared. That is a fairly large acceleration. That means for every second this skier is going down the slope, if they don't swallow them, they're going to gain 6.8 meters per second. They'd be going pretty fast really quickly. So that's our second answer on this one. I want to talk about this one real quick because it's actually on your review packet, and it's one that always stumps students every single year. And so I want to make sure we just sort of talk about it because it has to do with friction and what we're talking about. In this case, Jamal pulls a 150 Newton sled. Now, real quick note on that one, that is not its mass. We're talking about newtons, we're talking about the force of gravity on it. So in this case, the force of gravity is 150 newtons. And Jamal is pulling this thing upward with a force of 100 newtons this way. So it must be like a tension in a rope here. He's pulling it up at 100 newtons. And interestingly enough, we're told that it moves at a constant speed. If it's moving at constant speed, what do we know has to be true? Well, the sum of all the forces on it must be 0. Well, before we analyze anything else, let's break this force, that 150 newtons, into its perpendicular and parallel components. Again, just doing a little bit of trig. And do put arrows on this, by the way, because it is important. So that angle appears 28 degrees again. And now just doing some quick numbers. 150 times the sine of 28 and 150 times the cosine of 28. And solving it real quick, then we can actually solve the forces. So we get 70.4 newtons on this side and 132 newtons on this side. And so the moment we get those, we can solve everything else. What do we know? We know the normal force here has to be 132. And finally, if it's going at a constant speed, we know that some of the forces must be 0. Yeah, we know there's got to be a force of friction acting this way, because right now you've got 100 acting upward, you've got 70.4 going downward. This thing should accelerate upward, should be accelerating up the slope. There must be a force of friction acting on this thing. What does it have to be equal to? In this case, it has to be equal to 29.6 newtons. You're like, whoa, 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 where'd you get that from? Well, we know the sum of the forces have to add up to 0. In this case, we have 100 going up the slope. We've got 70.4 going downward here. This must be 29.6, so the sum of these two downward ones is equal to the force upward. Does that make sense? Some of the forces are 0. Normal force cancels out with this component. This component, along with the force of friction, cancel out with this towing force acting up. Now here's the part where it gets interesting. Jamal now lets go of the sled. Not riding it. He just sort of simply lets go of it. What do we have going on? Well, we've got the same force of gravity here of 150 newtons acting downward on it. But here's where it gets interesting. Yeah, there's still this force here. The normal force stays the same as it was before because those components are still the same. But what direction is the force of friction acting now? So up here, this thing was going up the slope this way. Now it's sliding down the slope. What's going to be true about the force of friction? It's going to be acting up the slope with a force, that's 132, believe it or not. It's going to be acting upward because it acts always against the slide or potential slide. It's going to be 29.4 going this way. And you might say, whoa, 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 wait a second. How'd you get that? Because we have the same two surfaces in contact, mu sub k is going to stay the same, and the normal force is the same, which means this quantity has to be the same. It's just acting in the opposite direction. Always acts against the slide. So what's the acceleration then? Well, if we break this into its two components again, and I'm just going to draw straight lines here quick so I can do it fast. We still have the 70.4 going down the slope. And we still have this part acting over here, which is 132 newtons. What's the net force on this thing? Well, if you work it out, look at this closely. We've got this acting down the slope, this acting up the slope. They're not equal to each other. So if you do F net equals ma, the net force in this case is going to be the 70.4 pushing it down the ramp, minus the force of friction, the 29.6 acting up the ramp, equals the mass of this thing, which is, if making gravity 10 again, must be about 15 kilograms. Because the force of gravity was 150 newtons. And if you solve this, 70.4 minus the 29.6, sorry, give me a quick moment, divided by 15 gives us an acceleration of about 2.7 down the slope. As I quickly write these out, there we go. All right. The last question is just a quick one, and you've got this situation which almost looks like an Atwood machine, but we've got one of the things is sitting on a table. What are the forces acting on it? Well, you got the force of gravity, so 98 newtons on the 10 kilogram. I used 9.8 this time. 9.8 newtons on the other 1 kilogram, and 19.6 on that one. In addition, you've got the normal force on that one because of the table pushing up. And yes, you've got all these tensions, and I just left those unlabeled because they're internal forces if we look at the whole system. Here's where it gets interesting. Why did I bring up this whole idea of mu sub k? Well, there is force of friction acting on one of these three masses. Which one? This one. It's going to be acting this way, and you could very quickly calculate it's going to be 3.92. And you might say, whoa, whoa, where did that come from? It comes from this. Force of kinetic friction is equal to mu sub k times normal force. And if you solve that, you're just going to end up with 0.2 times 19.6. I can't write any faster than this, I'm so sorry. Which is going to give us this 3.92. Now, how do we know the force of friction is acting this way? Well, if you look at the situation real quick here, you'll notice that this 10 kilograms is much larger than this 1 kilogram. So what's going to happen? This is going to accelerate downward. This mass is going to accelerate towards the right, and this one's going to accelerate upward. And again, we knew friction always acts against the motion or potential motion of the system. How do we figure out the acceleration? Well, F net equals ma. And here's where the interesting part goes on. This 98 over here is trying to accelerate the system sort of, or the top mass to the right. This 9.8 towards the left. And if you want to think about it, this 3.92 also to the left. So these two are acting against the 98. So my net force, 98 minus the force of friction, minus the force of gravity on the other one. How much mass is being accelerated? The answer is all of it. If we solve it then, you should get the acceleration of the system, which in this case is, oh, good grief, hold on. 98 minus 3.92 minus 9.8, all divided by the total mass, which is 13. Give me a second here. Divided by 13, which gives us about 6.5 meters per second squared. That should be enough to get you started on your homework for tonight. Good luck with that. Have fun, and we'll talk to you soon.